Mixed representation for the case of a fixed quadratic field. So just to remind you what the setup is. So E is a fixed elliptic curve over Q without CM. K is a fixed imaginary quadratic field. Okay, and then we have the sort of local factor of the functional equation, and this defines these P numbers. Oops. Okay, and then we had the counting function that we're interested in is just counting the primes up to x, such that they're good and so forth, but the field generated over Q by this P number is equal to the fixed imaginary quadratic field K. And so the way the strategy was to notice that, so we had kind of this set AP of K, which is the set of all the set of all traces where the pair pi bar was some kind of was in a factorization of the prime P over K, and this is for P in PK, which is the set of primes P such that P equals P bar sum pi bar, or pi, sorry, in OK. Okay, so the point was that the size, and we started, let's see. So the size of this was equal to the number of roots of unity of K. And the starting observation was just that Q adjoin pi P of E equals K if and only if pi is one of the, P is one of these primes that splits completely in K, and AP of E is one of the traces, okay, from the imaginary quadratic field. Okay, and so then what we were doing is FP. So we had FKR of P is supposed to be the probability, heuristic probability that R is one of the traces in the imaginary quadratic field. And from before we had FER of P. I'm just quickly trying to recall what we had. The probability that APE equals R. And then we were going to mix these. And the point was that you'd like to try to do this. So FEK of P might be that's just the sum of overall R and Z of the products. But this doesn't really work because probabilities aren't independent. Okay, and so last time we evaluated an expression for Fk R of P, and we had some closed form for it, and this led to an asymptotic formula for pi k R of x. This is asymptotic to some constant, explicit constant times root x over log x. Here we're counting primes up to x where the prime has where for some factorization in the field K, where the integer R is in APK. So we were estimated or gave account for the number of such primes up to X. Okay, we did that last time. So now, so the mixed model. And I just introduced this last time at the end. So the mixed model is sort of, okay, now again, I had some kind of growing sequence of indices here. So this is supposed to be the probability relative to n of the event that AP of E equals R, and I guess S is one of the traces in the imaginary quadratic field, okay? And we had some assumption regarding this, and what it was we put this equal to phi, let's say, E of CRP. We introduced these truncation parameters just to deal with the fact that one of these two Sato-Tate type functions is unbounded. So psi of RP is about R over 2 root P, except it's equal to, it's basically equal to that, except when P is, except when R is too big, okay? Or, okay, I should say it maybe like this. Yeah. Anyway, I discussed what these truncation parameters were last time. And then, so you have these two, and then you also have some kind of, so these two factors you assume independent, okay? So in other words, you part of the model, we have no reason to believe that these know anything about each other, okay? But we do have reason to believe that the mod n considerations know about each other. And the reason for that is when are Chebytarov conditions in a couple of fields not independent? It's exactly when the fields have an unexpected intersection. Okay? And the point is that there are a couple fields in the picture that have that in general do have an intersection. Okay, so we have the kind of Sato-Tate factor, and then we have this factor. Okay, and we're going to put, oops. Sorry, put an n squared here. Whoa, just wet. Okay. And then times Cp times omega k. Okay. Okay, so here we have this delta. I said what delta E K R S N is. I have this written down. Okay. This was this limit. It's a density. Times sum overall P, K, and X of the number, of a function that just, it's exactly equal, if it's only equal to, it's only non-zero if AP equals R, and if it is, then it just counts all this does is it's talking about the density of primes, relative to splitting completely in the Hilbert class field, and not dividing the level n, of course, for which AP equals R and for some pi prime in a factorization of P and K, pi plus the trace pi plus pi prime is congruent to S mod n. So I just want to emphasize something, and that's that if, it could be, this set could have size bigger than, for some values of n, this set can actually have size bigger than 1, okay? And the whole idea of the model is, if that happens, then it should be a little bit likelier to find that should make it a little bit likelier to find the trace S in the quadratic field. Okay, that's the idea. The same thing happened in the previous model with when we modeled this. Okay, we had to be a little tricky about it. We had to introduce these weights. This was exactly for this reason. Okay. So if I take the sum over all R and S mod n of delta E K R S n, this is equal to 1. Okay. Okay, so I think everything, and CP is just, CP is again just, you can just sort of factor this out and sum over all R and S and then divide by what's left. Maybe I should say, so the phi E of S or of equals 0 if R is greater than 2 root P, and same with phi K. Let's phi Y equals 0. Y is greater than 1. Just to make so this is really supported, and the CP is just chosen so that the sum over all R and S in Z. Now this looks like an infinite sum, but it's really going over a box. All right. It's really all taking place inside here. Okay. Of F, E, K, R, S, and P equals 1. Okay? So just to normalize the model to be a probability. Oh, sorry. I just said 1. I lied. What should it be? It should be this. Okay. Lang-Trotter deal with this a little bit differently. They introduce, kind of restricted intervals in for this function that that pin down a unique representative of a unique trace representative in A, K, and P. I found this to be a little bit. I think almost any way you do this, you'll feel a little bit puzzled sometimes. But anyway, okay. So what can we do now? Just as before, what do we do? So. Okay, let's try to guess what the answer is. So this one, in the previous two cases, we got 1 over 2 root P. That was kind of a one-dimensional version, okay? So what should we expect this CP to be asymptotically as P goes to infinity? Well, there are kind of two factors of 1 over 2 root P. So you might expect it to be 1 over 4P. And then again, proof. Riemann Sum for one of remember, those two factors are independent, so you can split it up like that, and it becomes just an independent Riemann sum for each one. Okay. So once we have that, then we're basically ready to finish this off. Okay. So thus. This F, E, K, R, S, N of P is asymptotic to something, omega K, phi E of so I did all that just to write this. Okay. As p goes to infinity. Okay, so what we want to do now is, before in the previous models, what I now did was took the limit as n goes to infinity. But we're not going to do that quite yet. First, we're going to do a sum, and we're going to sum on r equal to s, because the whole point is we're trying to estimate the probability that we want to do this sum over r and z of these. So we're kind of looking at the diagonal of this. Okay, so therefore, the probability relative to level n of the event that that a p of e belongs to, is one of the traces from the field k, is estimated by, we take the sum over all r and z of this expression evaluated with a diagonal when r is equal to r. So we have this omega k phi e this one? Yeah, might as well prepare for what we should be preparing for. Okay, so now we're going to go ahead and do what we did before. Namely, the first thing is to realize that this only depends on r mod n, of course. So we can fiber over residue classes mod n. So we sum over r0 mod n. And then this factor can be pulled out. Now, again, when I do this, I'm going to go ahead and only, since I've reduced the dimension here by 1, because I'm not having r and s run independently anymore, I'll of course just couple. I only need one n for this. So I'll keep this like this. And then once I factor that out, then everything else, and I can bring the omega k out, of course, like that. And then now I have the sum over all r and z, r congruent to r0 mod n of phi e. Oh, what did I say? Oh yeah, r. Phi k p times n over 2 root p, and then maybe out of that I'll factor another 1 over 2 root p. Okay, so I'm writing it this way just to get ready. And now again, this inner part here, if you kind of draw the picture and think about it, this is just a Riemann sum. These are the widths and so forth. This is a Riemann sum. For this function. That's what it is as p gets large. Okay? So this approach. So for large values of p, this is approximately this. So in the limit, that's what you get. And so then this is equal to. Sorry, this is asymptotic to. Now I'll go ahead and factor this out. Sum. Times, and then okay, this is just the integral. Negative 1 to 1. Phi e x phi k x dx. Okay, is that factor? Times, and then was there anything left? No, I guess that's it. Okay, right. Okay, yeah, right. This p goes to infinity. The asymptotic. And now, okay, so let's just give this a name. Let's just call this what do I call it? Oh, I have a name for it. This is kind of the infinite part of the constant because it's sort of it has to do with the joint distribution at infinity, which we assume independent. Well, there are these lights, but that. Okay. Hopefully. Oh yeah, that's visible. It's only not visible when I'm close. Okay. Okay. So now, so this is fixed, and now we want to. Now we're ready to try and estimate we're going to take n going to infinity. Okay. So now, so we'll see, so fact. Okay, the limit as, again, n goes to infinity by getting more and more divisible of this expression of n delta ek r0 n exists. Okay. This is going to be this is going to be the kind of finite part of the constant, and this is going to be the sort of most delicate arithmetic part, just like before. Okay. So once we have that, so if we know that, then this leads to. So FEK then should be just this limit right here as n goes to infinity, times all this other stuff. So it's omega k times so, and this leads to the conjecture. Pi e k of x is asymptotic to this. Where is this? Okay. Times. Okay. I forgot to kind of evaluate this though, because remember that in the case of I left it this way to kind of leave it pretty general, but in fact we know what these distributions are. This one's 2 over pi square root of 1 minus x squared, and this one's 1 over pi 1 over square root 1 minus x squared. So there's this kind of unexpected cancellation where this cancels with that, which is kind of nice, and then we just multiply this by this and get 2 over pi squared and then the length of the interval. So this really is just 2 over pi squared times the length of the interval. So this is just 4. And I again forgot to do something. What did I forget to do? So what did I forget to do? Really, this, I forgot to show the one step. This is supposed to be the sum over not all p, but p and pk of x, of this f pk of p. Okay. And so since we're going over p and pk, I need to include a factor. I need to remember the Chebyshev theorem for the Hilbert class field. Okay. So this is 2, and then there's an hk. Denominator. So this is kind of an infinite part somehow, and this is the finite part. Now what we're going to do is just discuss the finite part, because that's so I'll mention what that is, and then we'll be done. So for how do we know this limit exists? Okay, so for finite part. delta EK. Okay, so what we'll do for that is this. We have to mix the two representations. So we have rho EKN for fixed level goes from the absolute Galois group of the Hilbert class field to, oh, maybe I should be, I'm going to write it over there because I have more room here. So, sorry about that. Okay. Okay, so this is just restriction. This is an embedding, and then this this also, I guess, embeds into okay, so here, this embedding is just, rho E and cross rho K, and where this is the class field theory isomorphism on the Ray class field, and this is the representation of Galois on the torsion subgroup V. Okay. So okay, the main point is that. So first of all, these two factors here are actually correlated, and the correlation comes from the fact that these two fields here, Q join En and the Ray class field here, intersect. Okay, there's one place where we know they have to intersect, namely in the cyclotomic field. Because of the Weil pairing, we know the cyclotomic field, the nth cyclotomic field's in here, and we also know that it's in here, because this is an abelian extension of Q, so of course it contains nth roots of unity. So we know that those are both in there, okay. But the reason that we had to mix the two representations, the reason the finite part of the constant's tricky is because that intersection actually may be bigger, okay? It actually could be bigger. Okay. So let me draw the lattice of fields over here. Okay, we have and then we have intersection of these two. And then under here, we certainly have Q and N, and then down here we have Q. Okay? So, so this is, I'll write it out. This is the intersection of the two fields. And it could be the reason FE RP and FK RP are not independent is that this may be a proper extension or a non-trivial field extension. And there are elliptic curves. There are elliptic, so it's not always. You can find examples of an elliptic curve E and a field K where this for all n is just, it has equality, okay? In which case, okay, this model is easier, they are independent. But you can also find fields K for which for any elliptic curve E, this is actually non-trivial, okay? So, in fact, for So, well, just as a passing remark. So this is, I don't really understand why. These happen to be the two fields where there are more roots of unity, the two imaginary quadratic fields where there are more roots of unity than expected. To my mind, I haven't properly understood why it happens to be that corresponds to this case. To me, it's kind of an accident. I don't really understand. It's really a group. There's a corresponding commutator calculation that you do in GL2, or really in SL2, that's responsible for this phenomenon here. But I don't understand what it has to do with roots of unity. Actually, I didn't. Probably just because I haven't thought about it carefully enough. Okay, so now, so let's call. So because of this fibering here, no, we can say that. So I'm going to put an n here. Okay. Let me define that. So GL2 Z mod NZ cross sub n of OK and OK cross over OK cross is defined to be the set of all matrices sigma and elements here such that the determinant of sigma equals the trace from k down to q of u. Okay. Okay, so that's what this fiber here means. It's referring to this equality. It's a fibered product of groups. Okay. So I'm going to call this this group. Well, maybe I'll write it here. This group we'll call script G of n. Okay, that's kind of this representation here lands you into the group script Gn. Script G. Okay, there's a problem, and the nuisance is that sorry. What am I saying? I said trace. What am I talking about? Trace is additive. What should I have written here? Why did I write an n here? Okay.
Norm.
Thank you. Norm. Okay. Yeah. Right. Good. Yeah, right. So okay. And this is well defined even at modulo roots of unity, right? The norm of a root of unity is 1 in this case, no? Or an imaginary quadratic field. Okay? So this is well defined, and what we really want to gauge is to what degree the traces of elements here are equal to the traces of elements over here. So and this will kind of be what this finite part of the factor is. Okay? But the problem is here. I wrote T here and nobody objected, but really traces are not well defined. This corresponds to the fact that when you pick elements in the quadratic field, you can't take the trace of it, right? So that means we have to take a pullback. So this is. I said there was a nuisance. This is dealing with what I called nuisance 1. Right, so this pi is a projection from this group to this group, and we'll call this G tilde of that. Okay. All right. So maybe now I'm gonna I guess write over here. Oh no, I'll keep that. I'll keep that maybe. So we're almost done. This is a never-ending story. Is there a movie? Okay. So okay, G. Okay, so we have this representation rho E K N that maps G H K. It's a homomorphism into this group G of n, and then we have Gn tilde going onto this group omega k to 1 by this map pi. Okay, and then so we g of n, non-script g, is defined to be the image. Okay. And then g tilde of n is just defined to be the obvious thing, the full preimage of in here. The reason we have to take this is so that we can compute traces. Okay? And then we can talk about, we can reinterpret the delta symbol in terms of Chebytarov statistics. Okay, and then finally, I guess, maybe I'll call it G. T, maybe, or trace, is defined to be the set of all, sigma u in G tilde of n, such that the trace of the matrix sigma is congruent to the trace from k down to q, which is well defined, of u, mod n. Okay. So these are the set of things that are equal with trace. Okay. So so here's the important thing. The important thing that we need to know is this. It's a claim. So this is just the analog of what we did before to interpret this as a Chebytarov statistic, sum over R0 mod n of this, sorry, I guess I mean this. No. Oh, no. Sorry. Before I do this, let me just say this. Yeah. No, I'll just say it this way. Yeah. So R0 mod n of n delta, this factor that we wanted to evaluate, is just equal to n times this So this probability, this this function that measures some kind of probability distribution in the of the factorizations congruent to trace R0 and then sums them over R0's mod n. This condition is really a condition, a Chebytarov condition in the appropriate field here. So this is really, I'll just say that the proof is the Chebytarov applied to this composite. Okay. Sorry. Intersect. Maybe, this is over HK. Over HK. Sorry, over HK. Okay. Once we have that, then we can evaluate the limit. Just knowing that. So how do we evaluate the limit now? How do we know that this limit exists? This comes from the analog of Serre's open image theorem in this context. And this next statement just basically follows from Serre's open image theorem. And you can just deduce it from the fact that there aren't a lot of entanglements in the language that Professor Stevenhagen was using. So let me just say that. Okay, so. Okay, this guy. Okay. An inverse n of this picture. Where was it? Maybe here. get a sort of global representation. This is called the mixed representation. And so now you can start using, so this is, do I need to write this? Okay, compatible family, and then there's this. This is still omega k to 1. And the main, well, the real point is this, the fact. That's the fact. Okay, so this follows from Serre's open image theorem plus kind of you draw the appropriate diagram. So this comes from Serre's open image theorem plus plus only finite number of entanglements. So that means that there's an MEK in the natural numbers, so that there are various ways of saying this. One is that I plus actually let's say it this way, so that rho ek of this image. Maybe I should just call it G, of GHK, equals pi inverse, let's call this, call that var pi so I don't confuse myself, of G of MEK, where pi from G MEK is the obvious, is the projection. Okay. And in the same way, when you compute this constant, the constant will write. So I'll just say this. Delta EK is actually equal to. So here you have to do a similar analysis. You just get that it's this same Chebotarev statistic written. There's an ME part, and then there's a product over all the primes, not dividing L, not dividing ME. So you have kind of the MEK, times GMEK. So I'll just say this, and I'll say a couple of words about that, and then I'll move on to some other kind of survey of results about these. Of the same statistic here. Sorry. Yeah. And here, okay. Sorry. I said this wrong. Okay. So this is you have to be kind of careful here. You have to be careful. Okay. You have to be very careful. Yeah. Limit as n goes to infinity of the same statistic, L to the n of L to the n tilde trace over G of okay. And this is delta E. Okay. Just the reason, so this is part of what makes this whole business pretty delicate if you actually want to go ahead and compute these constants, because in the other cases, I've observed this sort of vertical stabilization that happened, where once you know that the representation mod, a multiplication by a prime